Okay, this is the lecture for Chapter 3, Section 3, Gravity and Motion. All right, we stated that an object's inertia, remember the law of inertia. What's in motion stays in motion, what's at rest stays at rest. If it's in motion, it's going to move in a straight line unless a force acts on it. Okay, so we stated that an object's inertia causes it to move at a constant speed in a straight line in the absence of a force. However, suppose forces do act on the object. How much deviation from constant straight line motion will such forces produce? Will it cause it to curve greatly? Will it cause it to move just a tiny little bit? To answer that question, we first need to define more carefully what we mean by motion. All right, motion of an object is a change in its position. We can characterize in two ways: by the direction the object is moving and by the object speed. For example, suppose a car is moving east at 30 miles per hour. If the car's speed and direction remain constant, we say it is in uniform motion or moving in a straight line. If the car changes either its speed or its direction, it is no longer moving uniformly, as depicted in Figure 3.5. B and C. Such non-uniform motion is defined as acceleration. So again, I'm gonna flip here for a second. Let's take a look here. Remember, we're talking about Newton's second law. F equals force equals the mass times the acceleration of the object. Okay, it's mass and it's acceleration. So then let's go back and look here. Acceleration. Remember, you guys, that acceleration, and it was talking about a car, so I'm going to stick with the car. Usually we're used to acceleration as speeding up. Oh, let's accelerate, floor it, and let's move fast. Okay, let's get a high acceleration. Acceleration is also slowing down. Any change in speed is acceleration. Remember, the acceleration equation, A, or acceleration equals velocity final minus velocity initial divided by a change in time. So any speed or time, any speed is going to change your acceleration, okay? Speeding up or slowing down. Also, when we change direction, we are accelerating, okay? When we change directions, we are also accelerating. So in the first example, we produce an acceleration by changing the car's speed. We can also produce an acceleration by changing an object's direction of motion. For example, we drive a car around a circular track at a steady speed of 30 miles per hour. At each moment, the car's direction of travel is changing, and therefore it is not uniform motion. Okay, because there's not uniform motion, we are accelerating. How do we produce acceleration? Newton realized that for an object to accelerate, a force must act on it. For example, to accelerate, change the direction of the mass whirling on a string, we must constantly exert a pull on a string. Similarly, to accelerate a shopping cart, you can see the picture down here. To accelerate a shopping cart, we must exert a force on it. In addition, experiments show that the acceleration we get is proportional to the force we apply. So if we apply a small force, it's going to move slowly. If we apply a high force to that shopping basket, it's going to move faster. It'll have a higher acceleration, okay? A lightly loaded shopping cart may scoot away under a slight push, but a push of the same strength on a heavy loaded cart gives it a much smaller speed, as illustrated in 3.6. Thus, the acceleration produced by a given force also depends on the amount of matter being accelerated. Now, real quick, a little refresher. Matter, mass is a measurement of matter in an object. Okay, so if we let's just draw a box here. That'll be the easiest thing, I think. The matter in this box, these little molecules, atoms, whatnot. Okay. The amount of these gives us our matter. Okay. Or gives us our mass. These little particles in here, the molecules, the atoms, and that's what gives us our mass. Don't confuse this, though, with density. Mass. Density is a measurement of how close the particles are together. Okay. Farther apart they are, the less dense. The closer they are, the higher the density. Mass is a measurement, though, of those particles in that the piece of matter we're talking about. So the amount of matter in an object contains is measured by quantity that scientists call mass. Technically, mass measures an object's inertia. The more inertia, the mass, or the more inertia, the more the mass, and vice versa. So the more massive something is, and I'll bring up physical science here for a minute. The more massive an object is, like your refrigerator in the kitchen, it's hard to get that thing to move because it has a large mass. It has a large mass, and that gives it more inertia. On the other hand, if it's easier to move a chair, you can slide a chair across the floor a lot easier. It's because it has less mass, and therefore the inertia is not as powerful, okay, or as strong. So mass does measure an object's inertia. The more inertia, the more mass, and vice versa. Because an object has mass, because an object's mass describes the amount of matter in it, the mass in kilograms is a fixed quantity. An object's weight, however, measures the force of gravity on it, a point we will explore further in section 3.7. Thus, although an object's mass is fixed, its weight changes if gravity changes. Okay? Weight changes if gravity changes. All right, so mass is the final quantity. We know what acceleration is: speeding up, slowing down, changing directions. Mass is the final quantity needed to understand Newton's second law. All right, and they write it a little bit different according to the equation F equals ma. That's the way I write it, but you could write it this way: acceleration equals the force divided by the mass. Doesn't matter. Okay. This law states that when a force F acts on an object whose mass is m, it produces an acceleration. Acceleration, according to the equation F equals ma. However, the second law's meaning is clearer if we write it A equals Fm. Or stated in words, the acceleration of a body is proportional to the net force exerted on it, but is inversely proportional to the mass of the body. This astonishingly simple equation allows scientists to predict virtually all features of a body's motion with A equals F divided by M, and with knowledge of the masses and the forces in the action. Engineers and scientists can, for example, drop a spacecraft safely between Saturn and its rings, or use a computer to design an airplane that will fly successfully in its first time it is tested. Okay, hopefully this helps you with this section. We will see you soon.